Welcome to pre-algebra. In this chapter we'll be talking about whole numbers and operations on whole numbers, and we'll introduce some rather simple equations involving whole numbers later in the chapter. Now, the operations on whole numbers, adding, subtracting, multiplying, and dividing, I'm sure you've had those topics before. But don't skip this part. We're really laying a foundation in terms of terminology and a style of your learning and my teaching, which will lay the groundwork for all of our future discussions. Well, before we get started, I want to tell you that an algebraic system is actually composed of three ideas that kind of blend together to give us the whole system that we're studying. And those three ideas are these: numbers, operations, and properties. Now, the numbers we're talking about in this chapter are whole numbers. Operations are like adding, subtracting, multiplying, dividing, and there'll be others that we'll talk about as well. Properties involve ideas that allow us to or tell us what we can do with these operations on those numbers. That is, suppose I'll just give you an example right quick. Suppose we're adding 5 and 3. Well, we can say 5 plus 3 is 8, or we could say 3 plus 5 is 8. That is, we can add a couple of numbers in either order. Now, that's a property, you see, and it's called the commutative property of addition specifically. We'll get into those specific names later. But it's the idea that we have numbers, operations, and properties involved in an algebraic system. Let's talk about numbers. Now, we'll start with a set of numbers called natural numbers, and natural numbers are illustrated like this. It's the set consisting of, and these symbols mean we have a set here, and the items that are between these symbols represent the items that are within the set. So the set consists of 1, 2, 3, 4, and so on. ... means and so on in the pattern that has been established. Now, if we just take this set of numbers, the set of natural numbers, and by the way, these are sometimes called the counting numbers as well as natural numbers. But if we just add the idea of 0, the element 0 to this set, we have the set of whole numbers. So whole numbers are the set consisting of 0, 1, 2, 3, 4, and so on. Now, a lot of times numbers are illustrated using a number line. Here's a number line that has whole numbers on it. Now, in using a number line, we can a lot of times illustrate the relative size of numbers, and that's what we want to talk about at this point. Now, to use a number line, by the way, we can identify the position of a number on a number line by just writing a dot or drawing a dot, and that dot is called the graph of the number. The number 5, for example, is in this position. So that dot is the graph of 5. Now, numbers that lie to the right, as we can see, the numbers get bigger and bigger as we go out to the right and smaller as we go to the left. So a number that is to the right of another number is greater than that other number. So 7 is greater than 3. 7 is greater than 3 because 7 lies to the right of 3 on this number line. And we have a little symbol for greater than, and it's this symbol. 7 is greater than 3. On the other hand, take another pair of numbers. How about 4 and 6? 4 is here, 6 is here. 4 lies to the left of 6. So 4 is smaller than 6 or is less than 6. We say 4 is less than 6, or symbolically it's 4 is less than 6. Now, you may forget which way the little arrow seems to point, but the little arrow always points towards the smaller number. And if you forget which way the arrow points and what it says, then you can always discover what it is like this. You can say, okay, I'm going to take a couple of numbers that I know the relative size of. Oh, like 5 and 2. Now, I'll just make the arrow point towards the small number, and I'll read it as I understand it. I understand that 5 is greater than 2. Oh, this symbol means is greater than. You see, so you'll never forget which is which in that way. Okay, so we have our two inequality symbols, and let's use them to describe the relative size of the numbers in pairs over here. How about 5 and 1? Well, once again, you could just say, well, I'm just going to make the arrow point toward the smaller one and it'll be fine, and that's okay. Another way to think about it, though, is to think about which one lies to the right or to the left of the other on the number line. Now 5 lies to the right of 1 you see, and therefore 5 is greater than 1. If 5 is to the right of 1 on the number line, then 5 is greater than 1. Now 17 and 21. 21 lies farther to the right than 17, so 21 is bigger than 17. Now we're reading this from left to right though, so we say 17 is less than 21. The little arrow points toward the 17, the smaller of the two numbers, and we read it as 17 is less than 21. 45 and 54. Once again, 45 would lie to the left of 54 on the number line, so 45 is less than 54, and notice the little arrow seems to point toward the smaller number. 101 and 99. Well, let's see, 101 would be farther to the right of 99 on the number line, so 101 is greater than 99, so we write the greater than symbol. And once again, the little arrow seems to point toward the smaller of the two numbers. Whole numbers are formed using digits, and there are 10 of them. I'm sure you've seen these before. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are our 10 digits, and those digits are useful in forming numbers. Now, when the digits are arranged in a particular pattern, for example, a pattern maybe like this, then we have a number. Now, notice that there are 5 digits being used here. It's customary in situations like this when 5 or more digits are used that a comma be placed in a position where there are 3 digits to the right of the comma. And we'll have more to say about the use of the comma, what it means, and so forth in just a little bit. But at any rate, each of these digits, because of its placement, has a certain value. And we want to talk about that place value here. The 2 is said to be in the ones position. And so that is its digit value. The neighbor, the 6, it has a value which is 10 times the ones digit. 10 times 1 would be 10. So the 6 is in the tens place. The neighbor to the left of the 6, the 4, has a value which is 10 times the tens digit. 10 times 10 is 100, so the 4 is in the hundreds position, or is the hundreds digit. 10 times 100 would be 1,000, so the 7 is in the thousands place. 10 times 1,000 is 10,000, so the 3 is in the 10,000s place. Now, each place value, along with the digit in that place value, gives rise to or contributes to the value of the overall number. For example, if we take 3 that is in the 10,000s position, that means 3 times 10,000, or 30,000. That is its contribution to the overall value of the number. The 7 in the thousands position means 7 times 1,000, or 7,000. 4 in the hundreds position means 4 times 100, or 400. A 6 in the tens position means 6 times 10, or 60. And a 2 in the ones position means 2 times 1, or 2. So each digit is contributing a certain value to the overall number, and when we add all of those values, we get the number that we have before, that is 37,462. Let's talk about digit value a little bit more and the use of the commas. Now, I've just put little dashes, little kind of underlines here for the various digits, right to left, and notice the separation. Every 3 digits has a separator with a comma, and all the way across from right to left. Now, here are the values for all of those digits. Now, each group of 3 digits, that is, each of these groups is called a period. These are periods. Each one is called a period. And each period has a name. The name for each period corresponds with the word that is at the right of each particular period. For example, the period at the right is called the ones period. And the word, you see, the place value at the right of the period is the ones place. In the next period, the word for the place value at the right is thousands. And the word thousands appears in every name within that period. So this is the thousands period. In the next period, we have the word millions. This is the millions period. and in the period to the left it's the billions period. And incidentally, the pattern continues on forevermore. We only have 2 digits listed here for the billions period, but there is a third digit, and its value is, let's see, the last one we have listed is 10 billions. 10 times 10 would be 100, so it would be the 100 billions place, you see, and then another period would follow to the left and so on. But let's talk about how these periods contribute to the naming of a number. It turns out that to name a number, to write the name for this number, we say the number that is in a period, and then we name the period in naming a number. And we start with the leftmost period that is in use here. So here we have the leftmost period is the thousands period. So what we say is the number 37 and the period name is thousands. So we say or write 37,000, and then we say and write the number in the next period. Now for the ones period, we don't really generally write ones, you see, the period name. We do for all of the others. So this number would be written as 37,462. Now I'm using a comma in the name of the number, just in the same place as I use the comma in the number written with digits. And this is a kind of an optional thing. You don't find that all the time in your textbook, but it is not incorrect to do this. And it kind of helps us to keep track of where we are in the number. Let's take another number. This one is much larger. We'll start with the leftmost period that's in use. This is the billions period. So we name the number, and then we use the name of the period. So the number is 5, the period is billions, so we say this is 5 billion, and then we slide our thinking over to the next period, name the number, it's 256, and then the period name is million. So we say 256 million. And then we slide our thinking over a little bit more. We're in the thousands period. We name the number 483, and then we attach the period name thousand. So 483,000, and then we slide on over to the ones period and we simply say 791. Now I have written each period name on a separate line here for emphasis, but generally we probably wouldn't do that. This would just be strung out in a more of a sentence kind of form. Well, the idea of periods and the period names and so forth can be used to actually write a number that we have written in words. You see, we have the number written in words. Now we want to write the digits in their proper place associated with these words. We have 609,948. Now notice that there is no comma involved in the problem, but no matter, we will go through and first identify the period that is used here, the very first or highest period that's used. And that period is the thousands period. Now what digits will go in that thousands period? Well, it turns out that the digits will correspond to the number preceding the period name. So we have 609 in the thousands period, and then we write that down. And then we proceed to the number that is in the next period. It turns out to be 948. So we write 948. Consider this somewhat more imposing number, and notice we don't have the place values here for us to go by. We just start with 35,052,000 and so on. Now we identify first the leftmost period that we're talking about. It's the millions period, and we write the number within that period. So we write 35 in the millions period. Now there are no placements for the period here. We know that eventually we're going to have a thousands period and a ones period, but we generally just don't write these blanks. We just follow up with writing numbers. And the next thing we look for is the next period name, and that's the thousands period. The number in the thousands period is 52. So we write 52 in the thousands period and then another comma. Now notice the zero here. We put the zero in because we know there are 3 digits within every period. And if we just put a 5, 2, and a comma, we would only have 2 digits. So we need that zero in here to hold that position. There are no hundreds within the thousands period. That is, there are no hundred thousands involved in this number. So we need the 0 to hold the position. And the next thing we do is follow up with the number that is in the next period. It's the ones period, and that number is 407. So we write 407. Now suppose we change the number just a little bit. Now watch the change. Instead of having million, suppose this word is billion. We would start in much the same way. That is, we would say, okay, I'd like to identify the first period to the left that we're talking about. We're talking about the billions period. Okay, and what's the number in the billions period? It's 35. So we write 35 in the billions period. Now we know we want numbers for the we need a millions period, a thousands period, and a ones period to follow this billions period. Well, as we look at our number in its written form, the next period that's named is thousands. So we completely skipped over the millions, and it doesn't tell us we don't have any millions, but we don't. There are no millions that are mentioned here. So we have to have placeholders for all of the digits that are in the millions period. We write zeros for all of the items in the millions period. And then we proceed as we normally would. We would write 52 in the thousands period and then 407 in the ones period to finish off the problem. When talking about very, very big numbers, it's not always necessary to use every digit. That is, sometimes it's more descriptive just to use an estimate of that real big number. For example, if we're thinking about the distance from the Earth to the Sun, we might say, oh, it's 93,278,426. But it turns out that that distance changes from time to time because the orbit of the Earth around the Sun is elliptical. So the Earth gets a little closer, a little farther away. It's more descriptive just to use a general idea of that distance and say, oh, it's about 93 million miles. Now the idea of taking an exact value using all of those digits that I was talking about before and then changing it into an estimate of the distance to 93 million is the idea of rounding. We are really just taking a specific number and we're identifying another number that's a little easier to manipulate that is in the neighborhood of the number that we started with. Now here's how the rounding takes place. We can think about it on a number line like this. So I'll show you a little algebraic way. I say algebraic, but it's just a little identification method of performing the same operation. But it's the idea that if we take a number like 238, and suppose I want to round this to the nearest 10. Now on this number line I've identified the tens. Here's 200, 210, 220, 230, 240, 250, 260 and so on. You see now to the nearest 10, where are we? Well, we can see just visually here that 238 is nearer to 240 than it is to any of those other tens. So to the nearest 10, 238 is equal to 240, to the nearest 10. Now, what about to the nearest 100? Well, here's 200 and there's 300. So to the nearest 100, now which one are we closer to? Oh, we're closer to 200 than we are to 300. So to the nearest 100, 238 is really nearer 200. All right, so rounding this to the nearest 100, we would get 200. Now here's how the situation works if we're using a little technique of just looking at digits rather than looking at a number line. It's not always convenient to manufacture a number line when we're talking about rounding. So here's what we would do. We would say we want to round 238 to the nearest 10. To the nearest 10. Now here's what you want to do. You want to underline the digit that you're rounding to. We're rounding to the tens digit. And then you look at the next digit to the right, just the very next one. And if that digit is either 5 or bigger than 5, then you make this a 0 and make that one digit larger. You see? And here is that case. We look at the next digit. Now, don't pay attention to this one. We just underlined it because we're rounding to that one, and we look at this one. That's all. All right, it's 5 or bigger than 5. So we just make that a 0 and make that one bigger. So it's 240, 240. And that's what we found up here. Now let's see, how about to the nearest hundred? Well, rounding to the nearest hundred means that we identify the hundreds digit and look at the very next digit to the right. Don't look at the 8, look at the very next digit. You see now this digit is less than 5. You see, if it's 5 or more than 5, then you make that one larger. If it's less than 5, then you simply make it a 0 and make that a 0 as well. You see, you're going to turn all these other digits into, all these digits to the right of the one you're rounding to, you're going to turn those into zeros. You see, and it's just a question of whether or not you leave this as a 2 or whether you make it one digit higher. That's all you're really asking yourself by looking at the next digit. And since this digit is less than 5, we leave it as a 2 and turn those into zeros. So to the nearest hundred, this is 200, as we found earlier. Let's look at another one. Suppose we want to take 3,499 and round to the nearest thousand. Well, we identify the thousands digit and we look 1 to the right. Oh, it's less than 5, so we're not going to change this digit, and those digits become zeros. So this becomes 3,000 to the nearest thousand. This number rounded to the nearest thousand is 3,000, and that means that it's closer to 3,000 than it is to 4,000, you see. All right, how about to the nearest 10? Well, if we're rounding to the nearest 10, then we would underline the tens digit. And kind of a tricky thing happens here. Here's the tens digit, and we look to the right, you see, and we see this number is 5 or larger than 5, so we're going to have to increase this digit by 1. We're going to make that a 0, but we need to increase this by 1. Uh-oh. But when we increase the 9 to a 10, we have to carry the 1 in the 10 over to this next digit. So this is really 3,500, even though we're rounding to the nearest 10. So 3,500 is 3,499 to the nearest 10. We talked earlier about a number line, and recall it was just a line that had some marks on it, and associated with the marks were some whole numbers. And in looking at the number line, we were able to establish an order relationship between any two whole numbers, and we did that by just looking at whether or not one would lie to the right of the other or to the left of another and so forth, and we could tell this less than and greater than idea. Well, we can think of a number line then as a picture that allows us to tell some aspect or to establish some aspect between numbers. And generally in mathematics, pictures that allow us to do that are called either graphs or charts. And we're going to look at a number of different kinds of graphs here, and we're going to talk a little bit about interpretation. The first one we want to look at is called a pictograph, and the prevailing characteristic of a pictograph is that little pictures are used to show a quantity of some kind. Now let's kind of look at the labeling on the pictograph, and we want to look at the labeling on all of these before we start with any kind of interpretation. But we're talking about net worth here for certain individuals that are along this side, and the net worth, the values here are in tens of billions of dollars. So each of these big dollar signs stands for $10 billion. Now, just by looking at a pictograph like this, just by looking at this picture, we can see that because we have more dollar signs here associated with Bill Gates, that Bill Gates has the largest net worth of all of these folks that are in this list. All right, and we can even tell the difference between any two of them rather easily. We can see that since we have one more dollar sign here in this row associated with Bill Gates, that his net worth is approximately $10 billion more than the person associated with this row, and that would be Larry Ellison. We can tell that these two folks have about the same net worth because of the number of dollar signs being the same for those two. So that's how we interpret using a pictograph. In this next one, we have a circle, and this is called a circle graph. Sometimes it's called a pie chart as well, for sort of obvious reasons, because the circle kind of looks like a pie. But this kind of graph allows us to see or compare individual items to the whole more clearly than many of the other graphs. So we can see, for example, which item in this group is the largest item. And by the way, let me back up a little bit. Let's look at the title here. Average annual expenses in a United States household. Okay, average annual expenses in a U.S. household. We can see that the largest piece of the pie is housing, and we can see how the housing amount compares to the whole. It's more than 1/4 of the whole. You see, we can kind of get a pretty good reference right quick for the comparison of any individual item to the whole. We can also compare individual items to one another. We see that the housing quantity is bigger than any others, and we know that without even looking at the number associated with it. We can look at the number, but we really don't have to in order to tell that housing takes up most of the expense. We can see that, let's see, transportation, that this item in the pie chart or the circle graph, this item is going to be more in quantity than an item, let's say, up here. So the transportation is more than the clothing, you see. And we could associate, again, we could associate numbers with those amounts as well. But circle graph. Here's another kind of graph. This is called a bar graph, and for sort of obvious reasons. All of these are named in sort of an obvious way. But the bar graph, we have bars here that associate certain numbers with one another. Now the graph is showing the length of the State of the Union address. How long did it take for the President to deliver the State of the Union address in these various years? You see, we have 1994, 1995, 96, all the way through the year 2000. And the number of minutes for each of those addresses are given here. Now notice the labeling along this axis is minutes, and down here we have years. And from the bar graph we can very easily see, because of how these stack up to one another, we can see which of the years contain the longest State of the Union address. We see that that was this highest bar over here. Now the number associated with it is 89 minutes. But maybe we just want to know which year had the longest address. And we see the biggest bar here. We see that that happened in the year 2000. And we can very quickly see that using a bar graph. We can see that the shortest State of the Union address is associated with the shortest bar, and that occurred in 1997. It happened to be 1 hour in length. Here's another bar graph. It's a double bar graph, and it's useful in comparing a couple of items. Well, let's just read it and see how useful it is. We have some names of automobiles down here, and we have some miles per gallon. So we have some mileage figures here in the bar graph. Now, miles per gallon, this would be 20 miles per gallon, 40 miles per gallon, 60 miles per gallon. I think you get the picture. Now, in double bar graphs like this, we generally have a different kind of shading feature on bars that are right next to one another. And usually there would be a legend associated with each of these shading ideas. And we can see from up here that the solid shading is for city miles per gallon, and the stripes are for highway mileage or miles per gallon. So let's see. For the Honda Insight, we have for city mileage, it was 61 miles per gallon, and for the highway mileage, it's 70 miles per gallon. And let's see, for the VW Beetle diesel, 42 miles per gallon for the city. You see, we have to refer to the legend now to understand what we're talking about for a particular kind of shading. And then we see the highway miles per gallon and so on, and we see that for all of the different automobiles. So we have miles per gallon on one axis, different names of automobiles, and we have this double bar idea associated with a particular legend. This is called a broken line graph, and it's entitled Enrollment in Elementary and Secondary Schools. And notice on this axis we have enrollment, and down here we have various years, 1970, 1975, and so on, through the year 2000. Now notice a little broken part to this axis. This line comes down and it's a little jagged in here. What that indicates is that the scale along this axis is not exactly accurate. That is, the distances here are not all the same all the way down to the bottom. We have 50 million, 40 million, 30 million. Notice that there's no 20 million and 10 million down here. That is the increment. The distance here is not consistent with the distances between these items. Now, that's only important because sometimes graphs can be misleading when that little jagged situation can occur. It could be a misleading graph if this were not there. At any rate, we have enrollment over here, we have years over here, so just looking at the graph we can tell when the enrollment was the smallest. Looks like it was the lowest here in 1985. We can tell that between the years 1970 through 1985 the enrollment was decreasing, and from 1985 through the year 2000 the enrollment was increasing. So those are different things that we can tell by looking at the broken line graph. Here's another broken line graph, and this one actually has two bits of information on it. This one is entitled Populations of California and Florida. Now, one of the graphs represents the population of California, the other represents the population of Florida. And we need some kind of legend or some kind of information to tell us which graph is which. And here it says that the dotted line is for California and the solid line is for Florida. We have population numbers along this axis. Now, notice no jagged line here because the distance here is for, this is three little units, but it's for 10 million and then 20 million, 30 million, 40 million, the same distance for all of those, so there's no need for that little jagged piece there on this graph. Notice the years, we have 1900, 1925, 1950, and so on. We have 25-year increments here for these population numbers. And what we're noticing is that the population in both states is increasing, but when putting two graphs like this on the same coordinate plane like this, the same display, we can tell the difference between the two. We can tell that the population of Florida was greater than the population of California in the year 1900, and they were about the same somewhere between 1925 and 1950, and it kind of looks like they separated quite a bit in the 25 years between 1950 and 1975, and they increased at about the same rate during the years 1975 to 2000. So we can read a lot of different things about two different graphs on the same coordinate plane. We can also tell something about the difference in their populations if we want to determine that. Now notice that we don't have actual numbers associated with each of these dots. In order to read the population number associated with a dot, we would have to kind of look at the dot and slide over to the left. That top dot over there is a little above 30 million. So the population of California in the year 2000 was a little above 30 million folks.